Chapter 1. The Science of Electricity and Electronics. Objectives. After studying this chapter, you will be able to identify the relationship between elements and compounds, construct a model of an atom, discuss the concepts of atomic weight and atomic
number,
state the law of charges and explain it using several examples, explain what is meant by electric current, voltage, and resistance, describe the two theories of current direction, distinguish the conductors, insulators, and semiconductors, and state and explain Ohm's law. Keywords and terms in this chapter. The following words and terms will become important pieces of your electricity and electronics vocabulary, so look for them as you listen to this chapter. Alternating current, ampere, atom, conductor, coulomb, current, direct current, electromotive force or EMF, electron, element, insulator, neutron, Ohm's law, ohm, potential difference, proton, resistance, semiconductor, volt, and voltage. We are fortunate to live in an age in which the opportunity exists to study the electron. New discoveries, developments, and applications in electronics occur almost daily. These open a promising vista of unlimited opportunities for the creative scientist as well as for the skilled technician. We are living in a truly electronic age.
Section 1.1.
The nature of matter. Everything in the universe is made of matter. Matter can be defined as anything that occupies space or has mass. Matter can be found in the solids, liquids, and gases. However, these states are subject to relative temperatures. Water is usually found in liquid form, yet water can be readily changed to a solid or a vapor form by changing its temperature. Matter can also be described by color, taste, and hardness, but these are only observable characteristics. They may not truly identify a substance. To truly identify a substance, the substance must be broken down into its smallest parts. The substance must be described in terms of its atomic structure. Only then can it truly be defined as its behavioral characteristics identified. A substance has been broken down to its purest form. When breaking it down further, will change its atomic characteristics. This form is called an element. There are over 100 elements. Most of these elements occur naturally in our universe. Some of the elements do not occur naturally, but have been created in laboratories. Some common examples of naturally occurring elements are iron, copper, gold, aluminum, carbon, and oxygen. Figure 1-1 is a periodic table. This table lists all of the known elements and describes them in the scientific terms that make them each unique. If two or more of these elements are mixed together, a compound is created. A compound can be reduced to its individual elements. An element can be reduced to its atomic structure. If the atomic structure is reduced, that element is changed to a different element. Molecule and the atom. If a crystal of a table salt is cut in half, the result is two smaller crystals of common salt. The composition of the salt crystal does not change. It is simply smaller. Salt is a chemical compound composed of two different elements. The elements are sodium and chlorine. Each of these elements, sodium and chlorine, are deadly poisons to the human body. But when combined, sodium and chlorine become the harmless compound known as common table salt. See figure 1-2. If it were possible for you to smash that crystal of salt into its smallest possible piece, you would have one molecule of salt. A molecule is the smallest part of a compound that still retains all of the characteristics of that compound. If you reduce that single molecule of salt into its next smallest form, it is no longer salt. It is now broken down into different parts. These two parts are the basic elements, sodium and chlorine. You have now created poisons out of the normally harmless salt. But do not worry, we have never known salt to be reduced at the dinner table. The smallest form of an element is known as the atom. The word atom is derived from the Greek word meaning indivisible. The atom is so small that it is difficult to visualize. If we attempted to fill a matchbox with atoms at a rate of 10 million per second, it would take over 1 billion years to fill the box. The atom is the smallest form any material can assume without changing its characteristics. See figure 1-3 for a chart and illustration showing the relationships of matter, compounds, elements, molecules, and atoms. Electrons, protons, and neutrons. To understand the mystery of electricity and especially the characteristics of solid-state electronics, we must have a basic understanding of the structure and forces that make up the atom. Physicists have discovered that atoms are composed of many minute particles. We will be concerned with only 3 basic parts of the atom. The structure of the atom, figure 1-4, is similar to our solar system. In our solar system, the planets Earth, Venus, Mars, etc. revolve around the sun. The planets whirl around the sun in their orbits, suspended in space by the effects of centrifugal force pushing them away from the sun, and gravitational attraction pulling them toward the sun. In an atom, the sun's place is taken by the nucleus in the center. Electrons whirl around this nucleus. While planets are held in place with gravity, electrons are held in place in their orbits by their attraction to the nucleus, overcoming the centrifugal force. The electrons orbiting around the nucleus display a negative charge. The nucleus displays a positive charge because it is composed of positively charged protons and neutrally charged neutrons that are neither negative or positive. The number of electrons and protons that make up a particular atom are usually equal in number. This equal number creates a canceling effect between the negative and the positive charges. The atomic structure of each element can be described as having a fixed number of electrons in orbit. Examples of the atomic structure of 2 common elements are displayed in figure 1-5. All elements are arranged in the periodic table of elements according to their atomic number. The atomic number of an element refers to the number of protons or electrons that make up an atom of that element. The order of elements may also be arranged by atomic weight. The atomic weight of an element refers to the approximate number of protons and neutrons in the nucleus. Referring to figure 1-1, note that the atomic weight of hydrogen is 1, or scientifically 1.008, and its atomic number is 1. The atomic weight of oxygen is 16. Its atomic number is 8. Ionization. Usually, an atom remains in its normal state unless energy is added by some exterior force, such as heat, friction, or bombardment by other electrons. When energy is added to an atom, the atom becomes excited. If the exterior force is of sufficient strength, electrons in the atom's outer rings or orbits can leave their orbit. How tightly bound these outer electrons are to an atom depends on the element and the number of electrons in the outer orbit. If electrons leave the outer orbit, the atom becomes out of balance electrically. If electrons leave the outer orbit, the atom becomes out of balance electrically. This concept is extremely important and will be repeated throughout this book and in your studies of electrical phenomena. When the electron leaves the outer orbit, the atom becomes ionized. Figure 1-6, an ionized atom is electrically unbalanced. An atom that loses an electron from its outer orbit has more protons or positive particles in the nucleus than electrons or negative particles in orbit around the atom. The atom becomes a positive ion and displays positively charged characteristics. When an atom gains an extra electron, it becomes a negative ion. Negative ions display negatively charged characteristics. The electron that has broken out of its orbits is negatively charged. This concept of negative and positive ions is a key building block to understanding electronic theory. Section 1.2, Static electricity. The word static means at rest. Electricity can be at rest. The generation of static electricity can be demonstrated in many ways. When stroking the fur of a cat, you will notice that its fur is attracted to your hand. As you bring your hand back over the cat, you will also hear a crackling sound. If this is done at night, you may see tiny sparks. The sound is caused by the discharge of static electricity. When we stroke the fur with our hand, the friction between the cat's fur and our hand excites the atoms. Some atoms lose electrons while others gain electrons. The sparks are created as the atoms attempt to neutralize themselves by gaining back the lost electrons. You can generate a static electric charge by walking across a wool or nylon rug with plastic-soled shoes. After walking across such rug, you will receive a surprising experience of discharging several thousand volts of static electricity to a metallic object, such as a door handle. This condition is especially present on cold
winter
days when the humidity is quite low. You can also experience a similar discharge when sliding across a seat of a car covered with certain types of upholstery. The friction of your clothing against the seat leads to a discharge when you touch the earth and the metallic frame of the car at the same time.
The law of charges.
One of the fundamental laws in the study of electricity is the law of charges. The law of charges states that like charges repel each other and unlike charges attract each other. Again, the law of charges states that like charges repel each other and unlike charges attract each other. The power of attraction can be seen when you run a comb through your hair several times. The comb will attract some of the hair toward itself because of the unbalanced electrical charge created by the friction between the hair and the plastic comb. Experiment 1-1, demonstrating the law of charges. These tests demonstrate the law of charges. The materials needed are 2 strands of suspended pith balls, 1 vulcanite rod, 1 piece of fur, 1 glass rod, and 1 piece of silk. Step 1 is to negatively charge the vulcanite rod with the piece of fur. Step 2 is to bring the rod close together to the hanging pith ball. Step 3 is to observe that the ball is first attracted to the rod because of unlike charges. When the ball touches the rod, it is immediately repelled. Continue to attempt to touch the pith ball with the vulcanite rod. Examine Exhibit 1-1A. Why has the pith ball acted this way?
Step
4. Recharge the vulcanite rod and touch it to the second pith ball. You now have 2 negatively charged pith balls. Bring the 2 pith balls near each other. Do your observations match those of Exhibit 1-1B?
Step
6. Charge up the glass rod by rubbing it with a piece of silk. Touch the glass rod to one of the pith balls. Leave the other negatively charged.
Step
7. Bring the 2 pith balls near each other. Do your observations match those of Exhibit 1-1C? If so, explain why you have just observed using the law of charges. Copy machines. There are many different copying machines available today. The copying method explained here is based upon the xerography system of copying. The term xerography is derived from the Greek xeros and graph, meaning dry writing. Xerography process uses powder toner, heat, light, electrostatics, and photoelectric phenomena to produce a copy. Recall that like charges repel
and
unlike charges attract. Now let's introduce a new electrostatic principle. When a strong beam of light strikes a positively charged area or surface, the light protons will dissipate the positively charged surface areas. Photons exhibit a negatively charged characteristic. This is the underlying principle of xerography. The original document is placed face down on the glass top of the copy machine. A positive charge is introduced on the drum surface and a negative charge is placed on the blank paper. As the drum rotates, a strong light source is moved along the glass just below the original. The light source is directed toward the original and then reflected back from the white areas through a system of optical lenses. The original document absorbs the light in the dark areas and reflects the light from the white or lighter areas. Shades of gray or colors that are seen as gray are partially reflected. The reflected light is directed toward the positively charged drum area through the optical lenses. The positive charge on the drum surface is neutralized by the light. Photon energy is negative. The areas not affected by the light are left with a positive charge on the surface of the drum. The toner is dispersed on the drum and is attracted to the remaining positively charged areas. The negatively charged paper passes under the drum, transferring the toner to the paper. The toner is fused to the paper as it passes by a heater. The paper is ejected to the outside collection tray. A color copier uses the same principles as described above, except it makes the use of color filters and 4 shades of toner. The 4 shades of toner are magenta, cyan, yellow, and black. These 4 colors are mixed to produce the different colors on the original. The light and optic systems use color filters to transfer the image to the roller and add the color toner in stages. Other refinements of copier systems
include
the use of electronics and advanced optical lens systems. The size of the copy can be enlarged or reduced by adjusting the distance between the optical lens and the image. Lightening or darkening the copy is achieved by changing the intensity of the light beam. Electronic counters are used to indicate the number of copies needed. Diagnostic circuits can also be used to indicate conditions such as paper jams, low toner, or an empty paper tray. Many machines can switch between applications such as copying, faxing, scanning, and printing. Advances in design also allow the user to print on different types of materials, labels, transparencies, and even envelopes. Some machines print simultaneously on both sides of the paper, reducing printing time and paper jams. Another experiment 1-2, examining electrical induction and conduction. These two short tests examine the law of charges using electrical induction and conduction. The materials include one electroscope, one vulcanite rod, and one piece of fur.
Step
1. Quickly rub the vulcanite rod with the fur. You have just placed a negative charge on the rod. Electrons have been transferred to the rod from the fur by friction.
Step
2. Bring the charged rod close, but do not touch the electroscope. The leaves in the electroscope expand.
Step
3. Move the rod away from the electroscope. The leaves drop back down.
Step
4. Examine Exhibit 1-2A. Can you explain what you've just observed?
Step
5. Recharge the vulcanite rod with the fur.
Step
6. Touch the ball on the electroscope with the rod. Observe that the leaves in the electroscope expand.
Step
7. Move the rod away from the electroscope. Observe that the leaves do not drop back down.
Step
8. Examine Exhibit 1-2B. Can you explain why the leaves behaved differently in this test? Discuss the concepts of induction and
conduction.
with your instructor.
The Coulomb.
The force of attraction and repulsion of charged particles was studied by the French scientist Charles A. Coulomb because an atom
and electrons
in particular are so very small, a charge of a few electrons, say a dozen, is almost impossible to measure. Consequently, Coulomb developed a practical unit for measurement of an amount of electricity. It is known as the coulomb. 1 coulomb represents approximately 6.24 times 10 to the 18th electrons. While the coulomb is used to describe the flow of electricity, it is not used to describe static charges. It is impractical to describe the very small difference in charges between two bodies using values so large. Electrostatic fields. The field of force surrounding a charged body is called the electrostatic field or dielectric field. The field can exhibit a positive or negative charge depending on a gain or loss of electrons. Two charged masses are shown in figure 1-7. Lines represent electrostatic fields of opposite polarity and the attractive force existing between the masses. In figure 1-8, two charged masses are shown with like polarities. A repulsive force exists between the charged masses due to the electrostatic fields. The field is strongest very close to the charged body. The field strength diminishes at a distance inversely proportional to the square of the distance.
Again,
the field strength diminishes at a distance inversely proportional to the square of the distance. Figure 1-9 illustrates the concept of strength being inversely proportional to the square of the distance. When two electrostatic fields are joined together, the electrons flow from the mass with an excess of electrons to the mass that has a need of electrons. Figure 1-10 illustrates this principle. The excess electrons from the body that is negatively charged to the positively charged body that has the electron deficiency. This transfer of electrons can be accomplished by touching the two bodies together or by connecting them with a material that supports the flow of electrons between the two bodies. This connecting material is known as a conductor because it conducts electricity.
Induction.
Charges can be transferred in two ways. One way is by direct contact. When a charged body, such as a glass rod, touches another body, such as the top of an electroscope, the electroscope takes on part of the charge of the rod. Another way of transferring charge is by induction. A charge is induced by bringing a charged object near another object. The glass rod need only be brought near the top of the electroscope to charge it. When an object is charged by induction, the object takes on the opposite charge as the rod. When the rod touches the object takes the same charge as the rod. Refer back to experiment 1-2.
Static electricity applications.
The principles of static electricity are used in industry to reduce air pollution. One piece of equipment used in reducing pollution is called the electrostatic precipitator. Most precipitators are divided into two parts, a charging section and a collecting section. The charging section can be designed in many different ways. It can be an assembly of parallel rods or wires, a screen pattern or bank of piping. Regardless of the physical design, the electrical principle is the same in all cases. Figure 1-11 illustrates the operation of the electrostatic precipitator. A grid of electrodes is installed into the stream of pollutants. The electrodes are charged between 45,000 and 75,000 volts, forming an ionized field or a corona around each electrode. A corona is an area of ion or static charge surrounding a high voltage conductor. The pollution particles become negatively charged as they pass through the corona. The negatively charged particles are then attracted to the positively charged collection plates. After the collection plates become laden with pollution particles, they must be cleaned. This principle of removing particles or pollutants from the air is used in industries
such as
concrete, paper, chemical, and coal-fired power generation. The application of electrostatics is also gaining popularity in residential use. Electrostatic filters are a part of the latest air conditioning systems. The principle of attraction and repulsion is also applied in the painting industry and in the manufacture of sandpaper. The painting industry sprays a positively charged mist of paint onto a negatively charged surface, such as the panels of an automobile. This procedure reduces the amount of overspray and saves paint. The sandpaper industry charges the backing paper with a positive static charge and the silica crystals, sand, or some other abrasive with the negative charge. The result is an even spread of granules over the surface of the paper. Basic electrical circuit. A basic electrical circuit consists of three main parts: a voltage source, a load, and conductors.
Again,
a voltage source, a load, and conductors. In figure 1-12, a basic circuit is illustrated. This circuit consists of a battery as the source of electrical energy, a lamp as the electrical load, and two wires as the conductors connecting the battery to the lamp. In the source of the circuit, the battery, a chemical reaction takes place that results in ionization. This ionization produces an excess of electrons, negative charge, and a depletion of electrons, a positive charge. The battery has two terminals. These terminals are connection points for the two conductors. One terminal is marked with a plus sign and the other a negative sign. These two markings are referred to as polarity markings. Not all electrical devices have polarity markings. However, when polarity is a critical issue, it will be marked on the device. The proper polarity must be followed to avoid damage
to equipment
and/or personnel. Lesson in safety. There will be occasions when you become confused while working on electrical projects and with unfamiliar devices. Anytime you are uncertain about connecting any electrical device, check with your instructor, manager, or expert in the field. Damage from an improperly connected circuit is usually instantaneous and cannot be reversed. A load is created when the electrical energy produced in a circuit is converted to some other form of energy, such as heat, light, or magnetism.
The load in the simple circuit
in figure 1-12 is a lamp that produces light. The source and the load should match according to the voltage rating. If the lamp is rated at 6 volts, then the battery should also be rated at 6 volts. If the battery is rated at a lower voltage rating, the lamp will appear dim or will not light. If the battery is rated at much higher voltage, the lamp will be damaged by the excess electrical energy. The conductors we are using are two copper wires covered with a plastic insulation coating. The copper wire provides a path through which the electrical energy can flow. While the plastic coating restricts the electrical energy to the copper wire, this makes the conductor pathway safe for personnel. This completes the description of the basic components of a circuit in which electrical energy is channeled by way of electrical conductors through a device where it is then converted to some useful form. Voltage. Ionization can be caused by forces such as heat, light, magnetism, chemical action, or mechanical pressure. This results in the creation of an electrical voltage. What is voltage? Voltage is the force behind electron flow. It is the simple circuit just described. The battery was the source of electrical energy. This battery has a rating of 6 volts. The volt, written also as V, is the electrical unit used to express the amount of electrical pressure present, or the amount of electrical force produced by chemical action inside of the battery. The term voltage is used to express the amount of electrical force in much the same way we use horsepower to express the amount of mechanical force for an automobile. Electrical pressure or voltage can also be expressed as potential difference, or as electromotive force or EMF. For our purposes, these terms mean the same thing. Voltage is usually represented by the capital letter E or V. Current. Electrical current is the flow of electrons. The amount of electrons flowing past any given point in 1 second is rated in the electrical unit ampere, or capital A. The coulomb is a quantity of electrons. The ampere describes the rates of flow of the electrons past any given point in a circuit.
Again,
the ampere describes the rates of flow of the electrons past any given point in a circuit. 1 ampere is equal to 1 coulomb of charge flowing past a point in 1 second. Compare a balloon filled with air to an electrical battery. In figure 1-13, the amount of air molecules in the balloon represent the amount of electrons or coulombs as pounds per square inch, or the psi of air pressure. The amount of air pressure
inside of the balloon
is expressed as pounds per square inch, psi of air pressure. In the battery, the amount of electrical pressure inside of the battery is expressed as the voltage rating of the battery. The rate of airflow out of the balloon is similar to electron
flow
or current from the battery. The current from the battery in the electrical circuit is the volume of electrons flow past a given point, and is rated in amperes or amps. Just as the air will continue to escape from the balloon until the balloon is empty, electron flow will continue as long as there is voltage or electrical pressure present in the battery. Resistance. All electrical circuits have resistance. Resistance is the opposition of the flow of electrons. Resistance is measured in ohms, and the electrical symbol for ohm is the Greek letter omega. The resistance values of elements and compounds differ according to the atomic structure of the material. A good conductor of electricity is anything that permits the free flow of electrons. A poor conductor of electricity is a material that will not permit the free flow of electrons. Extremely poor conductors are referred to as insulators. A semiconductor is a material that limits the flow of free electrons. A semiconductor is considered neither a good conductor nor a poor conductor of electricity. Semiconductor materials are at the very heart of modern electronic applications and will be explored in depth in Chapter 17. Some examples of conductors and insulators are listed in Figure 1-14. Note that the Earth can be a good conductor of electricity. There are many factors that determine whether or not the Earth will be a good conductor. The Earth's conductivity is primarily dependent upon its organic composition and on the minerals found in the soil at any given place. The amount of moisture in the soil also determines the amount of resistance in the soil. Moisture can affect the electrical conducting ability of many materials. It can even cause an insulator to become a good conductor. Take wood as an example to illustrate this point. When wood is dry, it is classified as an insulator, but when wood becomes wet or moist, it behaves more like a semiconductor. It is the outer ring of an atom that determines whether an element is a good or poor conductor. If the outer ring has only one electron, that electron can be freed from its orbit rather easily by an outside force. If there are many electrons in the outer orbit, the electrons are held tighter in orbit and they are harder to free from the atom. Elements that do not readily give up an electron are insulators. Figure 1-15 is an illustration of the copper atom. Notice how this atom has only one electron in its outer orbit. This electron can easily be freed by an outside force. Copper is an excellent conductor of electricity.